enhanced, and therefore the strength goes up. In the next slide, we see the exact same thing occurs in cold drawing. If we have a piece of material with equiaxed grains and we pull it through the die, now just pulling it in tension, we have a flow that occurs. It's going to be by slip phenomena in here, and we're going to get, again, the elongated grains, and these particular grains are going to be smaller in this direction than they were before, and they're going to retard slip. Actually, if we look at what happens now in a situation where we have a rolling operation or any one of the deformations that we have just covered, and we have the polycrystalline equiaxed grains being mashed down into this small size, we find that what really happens is we elongate the grains, we get new grains to form. That is to say, we have such an instability developed in the material that we are going to recrystallize the material. We're going to cause new grains to start to grow from nuclei, and those grains will grow larger and larger, and finally we can wind up with an equiaxed grain at the other end. Now this is what's going to occur in a hot rolling operation. That is to say, we're going to smash the grains down so they become real fine, but those particular grains are going to be metastable, and they're going to decompose, giving away to the new little grains that form, the recrystallized grains, which will not have any strain energy in them, and we will wind up with a product that's on the other end that's virtually annealed. I'd like to tell you a little story that I think will impress you on the importance and the ability to control this particular grain structure. On the first day, I illustrated the grain size by showing you a little red board, or board that had a ASM logo in the center. I don't know whether you noticed that logo or not, but it's this particular board, and if you could focus on just the center of it, what you would see is that the crystal size has been caused to become very tiny in this particular area, and it says ASM. And if you can catch that, then you notice that actually it's just done with grain size. It's not scratched in there. It's not overlaid with anything. It's just different crystal sizes. Well, I made this board about, I don't know, 39 years ago, and I've been lugging it around talking to students ever since. And when I'm home, it generally sits on my mantelpiece, or it used to. And I happen to have a son who's an artist. He does also, he was in college studying art, and he painted and crocheted and knitted and wove materials, and don't misunderstand, he's not a sissy. As a matter of fact, now he's married, has 2 beautiful children. But he was 19 years old at the time, and he came in one day and he said, "Hey, Pop," he said, "see that board up there?" He said, "Could you make all those little teeny crystals inside of a big crystal?" And my response was, which shows you that I'm an Amos, I said, "Bill, the little crystals are inside of a big crystal." And he said, "No, Dad, those little crystals are among the big crystals. And I want to know if you could put them inside of the big crystal." "Well, what the heck do you want to know that for?" And Bill says, "Well, if I could put the little crystals inside of a big crystal, I could make a picture." He's an artist, and artists see things differently than most of us do, and they're generally not Amoses. Well, I didn't know whether you could do that or not. I knew how to make the board that I made, so I said, "Well, I'll find out." And I went to the library. Obviously, it's going to say, but I couldn't find out. And I went to my colleague, Dr. Green. He knows everything about recrystallization, and I asked him, and he said, "I don't know." And so I went home and told my son, "Look, we don't know, but I have some labs on my little farm," and I said, "When you come home next summer, if you want to try, I'll let you try it in the lab, but you got to work. I mean, I'm not going to let you goof off all summer." And he worked all summer at this. I gave him about $18 that summer, something like that. But nevertheless, I had sent him back to college. But in that period of time, he succeeded in doing it. Now, I happen to have here the first thing that he ever did. And what he did was, he grew a single crystal of aluminum. And that single crystal of aluminum, he plastically deformed areas that were the areas that are the land masses of the Earth. And then he caused the land masses of the Earth to recrystallize. And so he wound up with this terrestrial sphere that's a single crystal, where the oceanic masses represent that single crystal, and the land masses are polycrystalline aggregate. Well, we thought that was pretty nice, and we didn't see that anybody had ever done that before. And so I advised him he ought to get a patent on it, and he did. He succeeded in getting a patent. So Cyril Stanley Smith told us once that it was probably the newest real art medium in metal since about 13th century. So we felt pretty proud of that. And he gave one of these things to Channel 67. That's educational TV. And they auctioned things off, and somebody bought it for $960. And he says, okay, for hereafter, anybody wants to buy one of those globes, since I'm the only guy in the world that can make them, it's going to cost you $1,000. Well, he didn't sell many of them, obviously. But he did something else, and I think this is even more spectacular. And what he did was, he then got into business. He wants to make a lot of pictures. So he wants to make a great big sheet of single crystal aluminum that he can plastically deform with his ballpoint pen. That's the way he does it. He just dents the surface where he wants new crystals to grow so he can make pictures. And you know, when you were a boy or a girl, remember lying on the grass and looking at the clouds, and you say, hey, that looks like a fire plug, and that looks like a hammer, and that looks like anything, you know, old Ford or something. You play that game? Well, he grows these, he makes these attempts to grow crystal sheets, and he rarely ever succeeds. It's a difficult thing to do. So he gets great big crystals, enormous crystals, and he etches them, and then he looks at them day after day, and finally he decides he sees a picture in it. And then he plastically deforms where he wants a new crystal to grow, and then he anneals it. He puts it in a furnace at 1115 degrees for 15 minutes, takes it out, quenches it in water, and when he does that, he has all these scratch marks, all of these indentations on the surface, and he polishes those indentations off, so he's back to the bare metal, back to the smooth metal again, throws it in a bucket of acid to etch the crystal structure, and he comes up with very, very beautiful pictures. Well, I have one of these pictures, and I thought you might like to see it, because it's a very unusual thing, and you probably won't see one unless somebody in my family shows you one. They're pretty hard to come by. But here's what it looks like. What he saw when he originally had his plate was one single crystal, almost one single crystal, with the exception of, in the foreground, this material. And this particular material you may recognize as dendrites. They're the shrinkage cavities in the top of his little casting that he made. He also had this crystal, which is now the sail of a boat, and this crystal. So he had all of this shrinkage cavity, a junk at the top, and these two things that he said, I'll make a little junk sailing vessel in between. And you notice now, if you tilt the picture, it talks to you. And so I have all sorts of scenes like this in my house that he has made. And I have one scene where it's called a lake scene, and he has an oak tree in it, and every leaf on the tree is another crystal. And if you walk from one side of my dining room to the other, the picture changes from a sunrise scene to a sunset scene. Rather beautiful, isn't it? So this has to do now with recrystallization as a result of deformation and increasing the temperature of the material. And he has to be very careful, because if he took it out the furnace and he scratched it while taking it out of the furnace, it's already at a high temperature, and that deformation would cause that scratch to recrystallize instantly, very quickly, and he would get a stray mark. So I have a world, for instance, where he made that little mistake, and we have a series of islands right off the coast of Africa that really don't exist, right? Well, I thought you might like to see that, and it certainly illustrates for us that we can handle the recrystallization in a rather acute manner. At least he does. In industry, we do it, and we do it with a lot more control, but we're not interested in making pictures as he is.
Cold rolling changes grain size and shape from equiaxed to elongated in the direction of rolling. Cold forming, stamping, or forging causes grains to orient in a direction related to direction of deformation. Cold extrusion produces a high strength in the direction of deformation by elongating grains into long, flat, and thin shapes. Cold drawing is similar to extrusion, but pulls rather than pushes material through the die. Cold working can create such instability that grains recrystallize.
We have other cold forming operations that we can utilize. And actually, if we look at this particular slide, and we see a drawing operation, a swaging operation. In this swaging operation, we have a bar that we run through a mill that's actually a hammer mill. It's just like the old blacksmith. We took a piece of material and forged it on an anvil. In this particular case, what happens is that the hammers, which are these two hammers, and situated inside of this ring, as it rotates and passes each one of these rollers, it forces the material, forces the little hammer down to bang on the material. So the material is advanced axially through that cylindrical array, and as it's advanced, this thing rotates rapidly, and it just hammers it from every side and keeps on making it smaller and smaller and smaller and smaller. So it's a way to make a round rod without pulling it through a die, right? And actually you can do appreciably more reduction in area at one pass this way than you could in wire drawing. Well, there are many ways to do extrusions, to do plastic deformation, and one of them is by extrusion. Now there are lots of different kinds of extrusions. Actually we have backward extrusions and forward extrusions and mixtures of forward and backward extrusion. And just to start with, I want to show you that this backward extrusion, let's pay attention just for a moment to a plunger that's going down and into a material that's sitting down below here and forcing it to run up the side of the piece like this. We can do this and squeeze it out. You see the punch and the die become a system that forces the material up through it. It just flows, almost like water, up through that particular die. It can flow out of the die cavity, way up along the side of the piece, and all of this is called backward extrusion. And it doesn't make any difference what the shape of the piece is, so long as it's flowing against the direction of the advance of the punch. We call that backward extrusion. We can have a mixture of backward extrusions and forward extrusions, where when the punch comes down, we have part of the material going backwards and part of the material going the other way. Now, in fact, what we are doing now is making a forward extrusion on this side of this mandrel and a backward extrusion on that side, where the advancing piece is in this direction. So it goes both ways, forward and backward, in these particular operations. Or you can have just a backward extrusion that looks like the next slide. Well, this is another forward and backward illustration of a different product that's being made, but the material is flowing both forward and backward, and still the punch is moving forward in both of these cases. But if we just looked at the forward extrusion, it would look something like this. This is a forward extrusion now, and we're advancing the punch onto the work, and the work is being moved out of the material, out of the die material. That is, it's being advanced forward, and is this particular material. It's moving in the same direction as the punch. And in all of these cases, that's exactly what's happening. We're pushing on the material and forcing it forward, just like the punch is moving, and that's called a forward extrusion. Well, we do extrusions, as I explained to you before. Every time we squeeze toothpaste tube, we're doing extrusion. Or if you run a cookie press, you're doing extrusion. And the only thing that the metallurgist does any difference is he works with a higher strength material, stronger dies, generally at a higher temperature, but he could do it cold. He can actually do this cold. There's one thing that's made cold I think is exciting to learn about, because we use the commodity so much and we don't pay much attention to how it's made. And I have a story to tell you that I think is just super fascinating, but it has to do with the next slide, which I think shows you that how we do